Hi, my name is Andrew Sheeran, and I'm an environmental engineering master's student at the University of Rhode Island, working under Dr. Craver and Dr. Goodwill. And I'll be presenting my study, which is in collaboration with the Rhode Island Department of Transportation, which uses a data-driven approach to enhance street sweeping in urban areas. Stormwater runoff is a major transport of pollution into surrounding water bodies, and street sweeping can be an effective way at reducing runoff pollution since there is a massive amount of solids and associated pollutants that accumulate on the roads during dry periods, waiting to wash off during an intense rainfall. And in recent years, technology improvements and better management practices related to street sweeping have helped improve reducing runoff pollution. However, many areas don't have a real method for deciding when and where to sweep. And so the goal of this study is to develop an optimal street sweeping model that uses collected data on road characteristics, pollutant loadings, and climatic conditions. For the methods behind this study, we'll be collecting street solid and stormwater samples and conducting a variety of different physical and chemical analyses on them. We'll also be calculating certain metrics that summarize the area around a road, such as land use, canopy coverage, impervious surface area, and road quality. And the idea is to figure out relationships between these metrics and our pollutant loadings, which will serve as a framework for deciding when and where to sweep. Looking at the map in the middle, you will see our study area, which consists of 8 different road segments in Warwick, Rhode Island. Each road segment is 1,000 feet in length and was chosen based on their differing characteristics in terms of the area surrounding the road. We use GIS to calculate the percent land use, impervious surface area, canopy coverage, building density, and road quality to summarize these areas within a 250-foot buffer zone around the road. Moving on to some analysis of our street solid samples, you'll see a particle size distribution from our first street solid collection. To collect the street solids, we vacuum strips across the road, and you'll notice that some areas have much more accumulation than others, and that's due to the fact that some roads were swept prior to this vacuuming run. This sampling event happened in May, so all of the solids and sands that accumulated on the road over the winter was still sitting there, with as much as 9,000 pounds per curb mile. To complete the particle size distribution, we used a dry sieving technique and divided the street solids into 10 different particle size ranges, ranging from gravel to silt. And we found that most of the street solids fell in the range of fine to coarse sand. In the top right, you'll see more of a chemical analysis of our street solids. We use an X-ray fluorescence analyzer to measure the elemental composition of our street solids among different particle size ranges. The results we have are standard for sandy samples, with silicon as the most abundant element, followed by iron and titanium. However, we did notice that in the larger particle size ranges, phosphorus was abundant, while in the smaller particle size ranges, heavy metals such as zinc, copper, or lead appeared. We also did a thermogravimetric analysis, which plotted weight loss against an increase in temperature to help us understand the moisture and organic content in our samples. We are still in the data collection portion of this study, and we will need to collect more samples in order to make conclusions. However, we did find some initial trends that relate land use to particle size. For example, residential areas show more abundance in smaller particles, while commercial areas are correlated to larger particles. Commercial areas also consistently yielded the most solid accumulation. Moving forward, we'll be collecting more stormwater samples, and we'll use a flow meter to determine how rain intensity impacts the transport of pollutants. As we collect more samples over the course of the year, we'll begin to understand some of the seasonal trends of pollutant accumulation. We'll also be evaluating street sweeper removal efficiencies based on different types of sweepers and accumulation rates. All of this data will help us create a robust optimization model to decide where, how frequently, and which techniques to use during street sweeping. Thank you for listening to my presentation.